Okay. So today we're talking about inflammation. And this is actually one of my favorite lectures. And the reason for it is, if you understand this lecture on inflammation, you'll probably have a fairly good understanding of most every pathological disease that you'll come across. Okay? Because Taryn, correct me if I'm wrong, every time you open up a cadaver, there's going to be some level of inflammation somewhere. Okay? I mean, if they had a mitral valve problem or an aortic valve problem, if they had liver failure, if they had kidney damage, right? They had breast cancer, prostate cancer, you name it, there's going to be typically some inflammation associated with some tissue that has a pathological disease state to it. Okay, so secondly, I don't want you to walk away from today thinking, got it, inflammation is bad. Stay away from bad, bad, bad. That's also not true, okay? So inflammation is usually a problem with most underlying, or usually at the root of most pathologies, or one of the underlying problems associated with most diseases. But inflammation in itself isn't a bad thing. So inflammation is part of the normal wound healing response. Okay? So we're going to talk today about how the body uses inflammation to try to promote healing. And that inflammatory process is key when there's damage to a tissue. But you want it to be acute inflammation. You want it to be temporally short. You mean it comes up and then it goes down over time. When inflammation is chronic, where it comes up and it stays elevated, that's where you have a lot of these problems. We see that with autoimmune diseases. We see that with lots of different types of cancer. We see that with hypersensitivity problems. So a lot of the diseases, arthritis, a lot of the diseases tuberculosis, these diseases all have inflammation within them, but it's never gone away. So many times clinically, physicians will treat inflammation by trying to suppress it, maybe for a period of time. How many of you have actually been pretty sick and you've had like a prescription of a pretty hardcore corticosteroid called prednisone? Okay. Now, most of you probably weren't on it for a long time, meaning years. You probably were on it and then you backed off almost immediately. Is that true? And in some cases, maybe you were on it chronically because you needed it chronically, but they say, let's take a break for a period of time because I actually need you to come off of it, and then we'll probably put you back on it. But we actually need you to come off of it for a period of time. Okay, does that sound more familiar? So depending upon the extent of the inflammatory problem, the preference, if you have to use prednisone, is to hit it hard and short, and then stop. Okay? Because it's a broad-based anti-inflammatory, and your body needs inflammation to go through normal healing processes. Okay? All right, so inflammation is valuable for wound healing, but chronic inflammation is where it becomes problematic. Okay, so that's kind of the take-home message for today. So let's dive into some of the details. As the story will go today, we're going to look at inflammation as part of the survival of the species. We have it as one of our defense mechanisms. It helps to promote healing, but it also helps us to survive. As an organism, we have to be able to eliminate anything that we don't want inside of us, any threat or foreign invader. This could be infectious agents, but it also can be damaged tissues. We want to heal them. We don't want them to stay damaged for a long period of time. So it's a protective mechanism. That's why we have it. It's part of our innate immunity because it's within our genetic makeup. We have this program of inflammation that is initiated and is facilitated in all of us, for the most part. Let's just pretend all of us are healthy, the same way every single time. It doesn't change. It doesn't adapt. It doesn't learn. It's not different the third time you have a cut from the 300th time you have a cut. Inflammation is the same response every single time. It makes it really easy to study for the first exam because inflammation is the same every time. Okay? So because it's the same every time and it's the same in all of us, it's part of our innate immunity and we're born with it. You don't have to learn about it. What I mean is your body doesn't have to be exposed to it. It doesn't have to be vaccinated or educated on what to do. It just knows what to do. You get a immunization, you're exposed to the antigen, so your body learns to make the antibodies. That's not part of the innate system. That's part of the adaptive system. Okay? So let's talk about our first line of defense. Part of our innate immune system are things like barriers. They're non-specific. Physical, mechanical, or biochemical barriers in all of us. Right? Our mucous membranes, our skin. Right? The enzymes that release. You have lysosomes in your tears. Every time you blink your eye, it flushes across your mucous membrane, and there's actually enzymes there to kind of combat any of the outside environment that might be problematic. So this is all part of our innate system, but our first line of defense. Now, our second line of defense is actually where inflammation comes in. So it is innate, it is biochemical, and it's not necessarily a barrier, but one might think of it as like a cellular barrier, because there are cells that respond in a very intentional way when they come in cross with a foreign invader, like a bacteria. So we're going to digest this slide here in more detail. But then the third line of defense that we'll talk about in the subsequent lecture is our specific immune system, otherwise known as our adaptive immunity. And there's two main branches here in the adaptive or the specific immune system. We've got a branch that makes antibodies known as the B lymphocytes, and then we have a branch that manufactures T lymphocytes and effector T cells. And so we'll look at those in a subsequent lecture. So the body's equipped with these defense mechanisms, and think of inflammation as part or key or critical to this survival. Okay? It'll fight foreign invaders, but it also stimulates healing of the tissue. Now, some terminologies. So in the back, Bill had mentioned there's some dolor, right? Or actually, you were referring to the color, right? So you're referring to the redness or the rubor. We've got 4 different categories of local characteristics in inflammatory tissue. We've got dolor or pain, rubor or redness, or like the color of the tissue, cal or heat, and then tumor or swelling, right? And this is from the Latin, so it's tumor, not like a cancer tumor, okay? Tumor from the Latin meaning swelling. So when you have an inflammatory event in a tissue, let's say you fall and you smack your arm against the ground or the wall or whatever, okay? Or you twist your ankle, right? There's pain. There's typically redness. It's actually warm if you touch that area, right? And then fourth is you get tremendous swelling. So what's going on with respect to inflammation? Well, we're going to see what's happening as we start looking at the vascular network, and then we look at the cells that are associated with it. So acute inflammation versus chronic. That's how we're going to separate today's lecture. And acute inflammation and chronic are very, very similar. All the same stuff. This is very easy. Ready, study, tip. Acute and chronic have all the same characters. It's the same storyline, right? It's just there's a short version, acute, and then there's a long version, chronic. And the only major difference, for the most part, is time. Chronic sticks around for a long period of time. Now, there's one additional cell type that we'll talk about. Remind me that I said that. And do you have your markers? I'm going to make a note here. So time is really the only major difference. And then the second major difference are what we call foreign body giant cells. And I'll come back to that. So I just want to make a note here that I got to remind you of foreign foreign body giant cells so that I'm accurate in today's lecture, okay? But I want to set this up and make it easy for us. If you learn acute inflammation, you already know chronic, except for maybe a couple of unique details. And the biggest one is time. And then the second one, you already know the answer to. I wrote on the board. Foreign body giant cells, which you're like, what the heck are those? Some of you already probably know because you've been reading, right? Which is awesome. That's why you read. Because now you kind of know where we're going with this. And you'll remember it better. Okay, so the upper right is a picture of a vascular network. That vascular network has a venular side, which is conveniently colored in blue. Okay? And then has an arterial side, conveniently colored in red. And this is the capillary network that's in between. And under normal homeostasis, you would expect that you're going to see some resident macrophages out in the tissue. They're called sentinel cells. So you write sentinel cells, okay? Resident macrophages. They're looking for foreign invaders. They're watching. They're hunting for anything that could be problematic to the system. But they're in a low population and under a steady state, under homeostatic norm, because you wouldn't anticipate that there would be something there. Okay? Now, we have a situation of an inflamed tissue for one reason or another. Body doesn't know why it's inflamed, it's just inflamed. It could be trauma, it could be bacteria, it could be a foreign invader. You just don't know. But does it matter with an innate response? It doesn't matter. It's the same response every time. So one of the first things that you do is you dilate the vasculature. As you dilate that vasculature, you increase blood flow into that area. And as you dilate that vasculature, remember back to 202? The inside of the blood vessels are lined with endothelial cells. And they form what are called tight junctions. They actually link ends from one cell to another. And they form a monolayer. And it is a semi-permeable monolayer, but for the most part, it's non-leaky. Well, as you dilate the blood vessel, you break some of those tight junctions physically, and you create gaps between the endothelial cells where fluid and solutes can leak out. And why do you do that? Well, you want these circulating monocytes to get out into the tissue bed to make sure if there's anything that's foreign there, they can go find it and kill it. We'll talk about how they do that here in a minute. But you have to have a mechanism to get them out, so you dilate the blood vessel. When you dilate it, you increase blood flow. Now you get more nutritional fluid leaking out to the damaged tissue, right? And that follows with the leakage of plasma proteins, and that's where the swelling comes from. So when you trip, twist your ankle, and you get inflammation, you're like, why am I getting all these macrophages? It's an innate response. It doesn't know if you fractured the skin or not. It doesn't know if there's an infection or not. It just knows that there's some trauma. I need to open up the vasculature, allow it to become leaky, have these cells move out into the tissue, do their thing. I'm going to get fluid out here too, nutrition, to support these cells moving out to the tissue. And then when these cells get out into the tissue, they're going to start making certain growth factors and cytokines that recruit other cells to come in and help to heal. Okay? So it all kind of begins with dilating the vasculature. Question?
Are the terms neutrophil and monocytes interchangeable?
The question is, are the terms monocyte and neutrophil interchangeable? And they are not. They're both white blood cells, but they're two different types of white blood cell, a monocyte and neutrophil. So they have slightly different roles and characteristics. But for all intents and purposes, both of them are recruited into the tissue during an inflammatory event. The neutrophils usually come first, and then they're followed by monocytes moving into the tissue. But as soon as the monocyte leaves the blood vessel, it gets into the tissue, we call it a macrophage. Yep. So that's where you get these different terms. You've been reading, and you're like, okay, right? That might have been one of the questions as you're reading, like, what's the difference between a monocyte, what's the difference between a macrophage, and then a neutrophil? So neutrophils and monocytes are both types of white blood cells. They're found in the bloodstream. Neutrophils will leave first, okay? Monocytes will leave second. When they leave and they enter the tissue, they become macrophages. And macrophages are the cells. Neutrophils have the ability to phagocytose, but macrophages really have the ability to phagocytose. Okay? Yeah, exactly. If it wasn't for macrophages, we'd all be dead already. I'm serious. You're like, yeah, you're old, but you would be dead too. Okay? So this happens immediately, and you know this. You've twisted your ankle on one of these horrible stairs, okay? And I'm sure it comes after some fancy remodeling effort when you used to know the distance between the steps and now they've changed it, right? The moment you twist that ankle, you can feel that tissue start to swell. Do you know what I'm talking about? You can feel that tissue start to swell. Some of you have broken a bone, right? You've broken your arm. Some of you have done it a couple times. After a while, you just get good at it, meaning you're like, it's broken, right? You're like, there's no image again. Don't worry. Been here before. I can just tell by the way it feels right now, it's broken, okay? I said, all this blood flow's going in right now. I can feel it hurts. Any way I put my arm, it hurts, right? You just know. So this happens instantaneously. It doesn't take long for the blood vessel to dilate. So we get these vascular changes, and then we get these, what we call these cellular contributions, where the cells are able to leave the blood vessel and go out to the tissue. Okay? Again, all of you are like, oh my gosh, this is all supposed to happen. This is the way it's supposed to be, because blood flow is important for healing. Okay? If you don't get these cells out into the tissue, you'll never heal that tissue. Okay, so what happens? We get vasodilation, and you get what we call a temporary stasis. I thought you said that blood flow increases. Blood flow does increase to the overall tissue, but as you dilate out the vascular bed, right, we have a large amount of volume coming in. You dilate out this capillary network, the blood that flows into the tissue is increased, but the blood flow through the capillary network slows down a little bit because you dilate them out and you actually open up more vessels. Okay, you open up more feeder vessels when you increase the blood flow to the tissue itself. You with me? So the analogy would be like, if you have older plumbing in your house, okay, when you're growing up maybe, not me, this might be somebody, you know, I've heard this from friends, they would be in the shower, right, and my brother, or their brother would, you know, flush the toilet, whether they needed to flush the toilet or not. Because then, like, the water now would be compromised on the flow, and you get burnt inside the shower, right? So the amount of cold water to that network actually sort of drops because you have two sources. So if you dilate the vascular bed, even if you increase blood flow to the tissue, the number of feeder capillaries goes up, and so the flow through that capillary bed slightly goes down, okay? Why is that valuable? Why would you want the capillary flow to be a little slower? So if it's in there longer, it can heal the tissue, the nutrients can get out. What else can get out? The cells. It's easier for the cells to migrate out if they're going a little slower. Okay? You know, we'll see this come to play here. I have a couple videos and some drawings that we'll talk about. We increase the permeability into the tissue bed. We talked about that. And then we increase what we call oncotic pressure in the extracellular fluid. So the oncotic pressure in the extracellular fluid is referring to the solutes that move into the extracellular fluid encourages water to follow the solutes. And now you get this leakage of water out, and you create basically a sink by which water wants to leak, or fluid wants to leak. And this naturally leads us to two things that are exited. We have transudates and we have exudates. And what's the big difference? So a transudate is formed when fluid only leaks out. Transudate is only fluid. An exudate is when it's fluid and protein. Plasma protein. Now the plasma protein that you don't want to leak, but it's really big, so it like won't, is called albumin. So albumin is made by the liver, And it usually is one of the plasma proteins that stays within the blood vessel. And its concentration then on the venous side of the circulation is very, very high. And so it creates an oncotic pressure sink on the venous vasculature where the water wants to follow solutes, high concentration of albumin, and that's why the venous circulation will reabsorb a lot of the fluid. Okay? So on the arterial side of the capillary network, we're losing a lot of fluid. On the venule side, we're actually collecting a lot of fluid. Question? Question is low level of albumin in the blood? Yeah, that would usually mean like starvation. Well, yeah, we'll see that later. Unfortunately, we'll talk about what's called Korsakoff syndrome. So, like, you know, the kids that have the distended bellies, there's basically their body's cannibalizing itself, meaning that it's burning protein in its own. It's breaking down its own muscle supplies to supply protein because the liver is so starved it can't actually manufacture albumin. So that's that distended. Do you guys ever wonder that when you were kids? Like, you know, you see these lectures and they're like these starving kids in whatever country it was, you know, or is currently still happening. And I remember as a kid always thinking like, it doesn't make any sense that they're starving, but they get these big old fat bellies. Like, nobody explained that to me. I don't know, maybe the volunteers didn't understand what's happening physiologically. But those distended bellies are because there's so much fluid out in the extracellular space because there's no albumin in the blood vessel to bring the fluid back. What's that? Ascites is more of distended veins. Yeah. Okay. Other questions before we keep going? Okay. So these chemicals that cause these changes, right? We've got vascular changes that take place, but how does the vascular change? Well, we've got some chemicals that are being released. And a lot of these chemicals get released due to trauma to the tissue. So for example, histamine. Histamine is found in mast cells. And so in a traumatic situation to the tissue, histamine can be released very, very quickly and it causes quick vasodilation. The permeability of the blood vessel goes up, meaning it becomes more leaky. That's what that word means. It becomes more permeable. Histamine causes an increase in capillary permeability as well as compounds or cytokines known as TNF-alpha and interleukin-1. So TNF-alpha and interleukin-1 are manufactured or released by neutrophils as well as tissue macrophages. So histamine dilates, neutrophils leave, monocytes leave, they become macrophages. They make TNF-alpha, they make interleukins, they cause the vessel to dilate even more. It's a positive feedback loop. It's an example of a positive feedback loop. Another compound known as VEGF, vascular endothelial growth factor, also manufactured by tissue macrophages, causes potent vasodilation as well as increased capillary permeability. And so you can see this picture on the lower left. Here's a cartoon drawing of endothelial cells with these tight junctions. And here's inside the blood stream. And here's a monocyte that if it wants to actually get out of the cell, it's going to have to find a way. Some small amount of fluid leaks out, but it's brought back in on the venous circulation because there's lots of albumin in here, and the fluid follows the solutes, and if there's a high concentration of albumin on the venous circulation, it'll reabsorb a lot of that fluid. But then look here. You increase the permeability during an inflammatory event, you create these larger gaps, you get more fluid leaking out, right, in the form of transudate, and you get cells and plasma proteins moving out in the form of exudates. So the way I keep it straight is exudate, I think of exit. And cells and proteins are exiting with exudates. In transudate, it's just the fluid, okay? Like transmission fluid. So you're like, what? That's how I remember it. Okay. Question?
So exudate, transudate happen at the
Yes, they can. Or if there's no exudates, because the permeability is not high enough, it might just be transudate. But once exudates are happening, fluid's leaking at the same time. You with me? You can have transudate without exudate. You usually don't have exudate without transudate.
Say that one more time.
You can have transudates, fluid only, without any exudate, which has proteins or cells. But if you have a hole big enough for exudates to come out, you're going to have fluid coming with it. Okay? Question?
So the cytokines and TNF alpha and what was IO?
Interleukin.
Interleukin.
Interleukin
They're
1.
all produced by macrophages?
They are. Neutrophils also will manufacture interleukins. Okay, let's go back to this diagram, and then I've got a little video to show you that'll help, I think, describe what's taking place. So there are some critical steps in this process where we've got to recruit the cells that we want to leave, the neutrophils and the monocytes to become tissue macrophages. We need to activate them, get them turned on, ready to go do their activity. And then they have to move to the target, which is called chemotaxis. Let's pretend for a moment that there's an infectious agent there, or bacteria. We want them to chemotax to that agent. Even if there's not bacteria present, we want them to chemotax to the damaged tissue. We want them to move to the area that's relevant. So we've got a couple of different phases that takes place. Okay? These are endothelial cells up top, endothelial cells on the bottom. We have an inflammatory event outside of the blood vessel in the tissue, and we're going to recruit, activate, and then chemotact to the site. And there's a couple of steps that are important. Is first, these white blood cells, whether it's a neutrophil or a monocyte, they actually start to roll. Okay? They roll along the inner lumen of the endothelium. And then at some point, they get stuck, and they're called tethered. So it really should be rolling and tethered instead of tethering and rolling. I would switch those two words if it was me. Because the rolling happens first, and then they become stuck or tethered. As they become stuck and tethered, they activate. As they activate, then they move across the endothelium into the outside tissue. Once they get to the outside tissue, they see a chemical gradient, and they move towards that chemical gradient, and that's called chemotaxis. Okay, so here, we've got a cell. It starts to roll, eventually becomes tethered and stuck. Okay, maybe that's this picture somewhere in here. And the phase of rolling is initiated by these molecules known as selectins. So selectins are molecules that are expressed on the cell surface, and they bind to ligands on the endothelium. But they don't have a very strong bind. Okay, it's a weak bind. And so with the blood flow pushing them, it breaks. And when it breaks, they start their roll process till the next selectin. And it breaks, and then it rolls again to the next selectin. That rolling process upregulates selectin expression as well as integrin expression. Right? And then the integrins come in, and when the integrins bind, they get tethered. They don't move. And that's the strong bind. So it starts with selectins. As those binds break, it upregulates more selectin expression, and it starts to turn on integrin expression. When the integrins bind, then the cell sticks to the endothelium. Make sense? As it's stuck with integrin expression, it's going to start to what's called extravasate, or it's going to diapedese is another word for it. You might have seen those two different terminologies. Or migrate across. It leaves the vasculature. There's like 3 or 4 different terms depending on what textbook you read or what tutorial you're watching online, but they all mean the same thing. Diapedese, extravasate, leave the vasculature, okay, migrate across the endothelial barrier. They're squeezing out. All right, so let me show you this video I had queued up. Okay.
At sites of inflammation, chemokines secreted by endothelial cells bind to the extracellular domains of G protein-coupled membrane receptors.
Oh.
This binding causes a
Seriously, you guys know what's gonna
change
tell me?
in the cytosolic portion.
It was all queued up and everything. No one even said anything. I'll have to figure it out here in a second. Oh, man. Duplicate. Better.
At sites of inflammation, chemokines secreted by endothelial cells bind to the extracellular domains of G protein-coupled membrane receptors. This binding causes a conformational change in the cytosolic portion of the receptor and the consequent activation of a subunit of the G protein. The activation of the G protein subunit triggers a cascade of protein activation, which in turn leads to the activation and clustering of integrins inside lipid rafts. A dramatic conformational change occurs in the extracellular domain of the activated integrins. This now allows for their interaction with ICAM proteins displayed at the surface of the endothelial cells.
Okay, so the ICAM is on the endothelium, the integrin is on the white blood cell. Make sense? Okay?
These strong interactions immobilize the rolling leukocyte at the site of inflammation. Additional signaling events cause a profound reorganization of the cytoskeleton, resulting in the spreading of one edge of the leukocyte. The leading edge of the leukocyte inserts itself between endothelial cells, and the leukocyte migrates through the blood vessel wall into the inflamed tissue.
So did you see how the artist's representation of it was rolling? Right, so as it's rolling, that's selectins, okay? Surface expression of selectins binding to each other, but then breaking because it's under flow until the integrins bind. Okay, you guys want to see that one more time? I like some of you like to have these little pictures in your head of what this looks like, okay? That's why I'm not having you watch like 8 minutes of video.
To the
It's
extracellular
just these few
domain of
seconds,
the
okay?
activated integrins. This now allows for their interaction with ICAM proteins displayed at the surface of the endothelial cells. These strong interactions immobilize the
See the
rolling leukocyte.
red blood
at the
cells
site of
flying by?
inflammation. Additional signaling events cause a profound reorganization of the cytoskeleton,
This looks like an alien
resulting
movie
in
right
the
here.
spreading of one edge of the leukocyte. The leading edge of the leukocyte inserts itself between endothelial cells, and the leukocyte migrates through the blood vessel wall into the inflamed tissue. Rolling, activation, adhesion, and transendothelial migration are the 4 steps of a process called leukocyte extravasation.
Okay. Questions?
Rolling.
Pardon?
Rolling, I don't get.
You don't understand rolling?
Yeah, I don't get.
Okay. So, these cells are spherical. They're inside a tube that has blood flow. If they're going to stick to the surface weakly, and that bond is going to break, when they let go, they're going to start to roll because they're round.
Then why would they want weak bonds in the first place?
Well, the weak bonds, when they break, triggers the cell to upregulate the expression of more selectins and, more importantly, integrins so that they stick. So why even waste the time with that? What happens if a cell accidentally bumps up against an endothelial cell? Because blood flows all the time, right? Do you think your white blood cells accidentally bump up against endothelium on occasion? Yeah. So when they do that, if they don't do it repetitively, you don't get integrin triggering. So you don't want just accidental stimulation of inflammation, right? So you want to have kind of a process where it's selectins that are expressed to a certain level. As those bonds break, now integrin expression goes on, and then the integrin expression is what actually stimulates the recruitment or the sticking of the cell. Otherwise, you're going to have rampant inflammation when you don't want it. So it's sort of a checkpoint, if you will. Does that make sense? Okay. What else? Yes?
It said in the PowerPoint somewhere that monocytes are only in the vessels for a couple days and then they're gone. So they reproduce more or whatever and then is that true? Am I reading that?
They're recycled pretty quickly. Yeah, it is days.
They're
Yeah.
just on like call for whenever inflammation is needed.
That's correct. They're manufactured on a regular basis if they're not used. They're recycled. Their parts are recycled and they're remanufactured.
So integrins are on the surface of white blood cells, are selectins as well?
No, selectins and integrins are two different things.
Yeah.
So a selectin is a surface adhesion molecule, and same with an integrin. But the selectin surface adhesion molecule, its binding is not as strong as an integrin binding. They're both found on the surface of the cell. Just integrins are correct. White blood cell.
Because selectins have such a weak adhesion to the macrophage, that allows the macrophage to roll around the endothelial structure.
Yeah, when they're inside the cell, they're not quite yet called a macrophage. They're called a monocyte. But it's technically the same cell. It's just, we call them monocytes when they're in the vessel. We call them macrophages when they're outside the vessel. I just don't want you, I'm only correcting you so that you remember that. That's all. Yep. I think everything else that you said is accurate. Okay. All right. Let's keep going. Okay, so this is just another picture of the same topic, okay? Just another image in a little bit more detail with a few more terminologies. So there's lots of different ways to say the same exact thing. I will try on the exam to not be confusing and to try to define as many of the terms as possible. But, for example, if you see the word diapedesis, I will likely try to define it next to it like transmigration or extravasation, okay? If you have a question about do you mean by diapedesis, are you meaning like the cell leaving the blood vessel? And I'll say yes. But if you say to me, can you define diapedesis? Like if you don't know that word, you want me to define it, I won't be able to answer that question. But if you're getting tripped up, it'll be clear to me if you're fishing for an answer or if you actually are just getting confused by the word. Does that make sense? So my goal is not to confuse you, but my goal is to make sure that I test your knowledge. Okay, so ask me the question on the exam, and the worst I can say is I can't tell you that, right? So don't take it personal and be all pouty, okay? Don't be a hater that I didn't answer your question. But go ahead and ask the question, like, what do you got to lose? Okay? My goal is not to confuse you with fancy words, but when you're exposed to these words, you should be remembering the vocabulary. And that's why I'm using multiple terminology, because depending on what edition of the book you have, or where you're getting information online, it may be referred to different things. So here's a new term, margination. What do you think margination means? What do you think margination is referring to? Some of you that read, what do you think it means? Yes?
A space between the leukocyte and the endothelial wall.
The space between the leukocyte and the endothelial wall, right. Moving to the margin. So instead of being in the middle of the blood vessel, these cells during an inflammatory event, they start to move towards the wall. They marginate to the margins, right, of a page, the edge of the page. So that's all that word means, is margination. So if I asked on the exam, put these things in order of how they happen, You know what margination means, right? We just defined it and explained it. Rolling, tethering, right? The one slide a couple ago, right, again, says tethering and rolling. This came from some other textbook. Is this inaccurate? No, but I actually think this is more accurate. Rolling happens first, and then tethering. Okay, but this is just my weakness. This is more accurate. So if you're looking at the slides and you're not looking at, you're not watching the lectures, like at home, you're not watching these lectures, hi. Or you're not coming to lecture, you may not understand that the sequence is actually pretty important. It's not that this slide is wrong, it's just it's not correct. Okay. All right. And then adhesion, right? So here here's our leukocyte, right? We've got this green structure known as a Siala-Lewis X-modified glycoprotein. And then we have the integrin here, what we call a low affinity state, right? So it's like this. I'm not going to do anything, okay? And here we've got our selectin molecules. These selectin molecules on the endothelial cells bind to the glycoproteins on the leukocyte, but they don't stick very well. And as they break, you can see the arrow, the leukocyte actually begins its rolling process. Well, when it finally sticks is when the integrins move into this high affinity state. So instead of having kind of this surface molecule that looks like this, it's like this, right? And here it's in this high affinity state, and now it's binding to the ligand, which is called ICAM, okay? Intracellular adhesion molecule 1. This is the integrin ligand. The ICAM is found on the endothelial cell, the integrin is found on the white blood cell, and this thing now sits down and is stuck. And as it is stuck, this is going to start to extravasate, transmigrate, diapedese into the extracellular matrix. And it's going to follow this chemical signal as it moves to the microbe. Okay? So a little bit more detail. This is, I think, out of the 8th edition, out of your textbook. Okay? It's more complicated, it's got more stuff going on, so that's why I built up to it. Questions?
No, I think
Think you got it? Okay. SI is a great place to walk through these steps. Make sure you understand them. Make sure it makes sense. Okay? It's a lot of detail, I know, but it's fairly straightforward. Okay? The link 634 is the part of that video that I went to. You go to the link, I think it's from Harvard University, go to 6 minutes and 34 seconds, and that's where I started the video. You can watch the whole thing, there's nothing wrong with that. Wouldn't be necessarily a bad thing. Okay. Questions? Let's do a, go ahead.
What's the difference between adhesion?
Tethering and adhesion is the same thing. Thank you for asking that question. You were like, that might be a dumb question, I don't want to do this, right? Same thing. Thank you for asking. Tethering and adhesion is the same thing. Okay? 2 words for the same process. Just like diapedesis and transmigration. Okay, so now we've got a macrophage out in the extracellular matrix. That was kind of painful, but I think I followed you. Okay? And now what does it do? Like, it's there. What's it going to do? Well, now it's going to go kill the bad guys. I'm serious, okay? So how's it going to do that? Now this monocyte is in the periphery, and it's a tissue macrophage, and it's going to engulf the bacteria. It uses what's called a toll-like receptor. So a toll-like receptor refers to a phagocytic receptor like this that binds in a fashion where it creates a pit, and then this pit actually pinches off. But it pinches off and brings it in. It internalizes it. And so as it does this, it's signaling for opsonization. Opsonization is the step before phagocytosis, where it's referred to as cellular eating. Phagocytosis. Okay? Eating a cell. Or cellular eating. So as the cell ingests the microbe, it fuses with the lysozyme that has enzymes in it. The enzyme, lysozyme, fuses with the phagosome, and now you have a phagolysosome. These enzymes can interact with this microbe and either digest it and or can stimulate the production of nitric oxide through an inos, taking arginine to nitric oxide, or through a phagocyte oxidase that can take oxygen and make reactive oxygen species, which are lethal. But again, this is happening inside of the cell, inside of a package where it's contained. Okay, so this battle is happening in a lipid inner envelope. And that digests away the microbe and gets rid of it. And we refer to this as respiratory burst. Why? Because you're using oxygen to go kill microbes. So there's a respiratory process in the form of the production of, or the cleaving of oxygen into a free radical. And you use that as a self-contained mechanism in order to digest away and kill the bacteria. Now, what happens if the tissue, so this is what normally happens. This less desirable effects, and there's all this white space for you to write something. When would this go bad? That would be when there are less desirable effects, right? It's just a thing, less desirable meaning it's going to go bad. So this is what normally happens, but what do you know about infected tissue? What's happening in infected tissue? Which is winning, the bacteria or the macrophages? The bacteria in infected tissue, right? If it's a chronic infection. So if the bacteria wins, it gets to this point, but it can't overcome the bacteria, and now the bacteria takes over the cell, and as the cell dies and goes through necrosis, what happens to the ROSs? They get released. And if the ROSs are harmful to bacteria, that's why you contain it in the cell. What happens to the surrounding tissue when the macrophage is actually compromised? It gets progressively more necrotic, right? So this less desirable effect is in a chronic infection. You get all of this tissue damage that's due to the reactive oxygen species leaking out into the tissue. And you see that with chronic inflammation. So here you can say this is an example of what might happen in a condition of chronic inflammation. Not acute, but chronic. And that's where a lot of the pathologies take place. So you've got the normal rolling, tethering, or adhesion. You got the diapedesis, or immigrating. Here's another word, immigrating out. Okay, that's controversial in Arizona right now, I guess. And then you got the tissue macrophage, and it's activated, and if it sticks around for a long period of time, you've got chronic inflammation. And if you've got chronic inflammation, look at all the tissue injury that can happen. You've got toxic oxygen metabolites, that's reactive oxygen species. You got the dumping out of proteases. You got the dumping out of chemotactic factors, coagulation factors, amino acid metabolites, and nitric oxide. And then over on the fibrotic pathway, this is another word for scarring. A lot of the growth factors that the macrophages make, if they make them chronically or if they dump their contents in large concentrations, they're going to stimulate tissue fibrosis or scarring. That's another word for fibrosis. Does this make sense? Here's a picture of a macrophage, and I'll get to your question. Okay. What you're looking at, this came from Harvard. You're looking at a scanning electron micrograph of a leukocyte migrating across the substrate, which is pretty cool. So the macrophage is actually moving this direction. So it's reaching out, and then this will follow, and this is like the butt end or the tail, and this will eventually come from lower right to upper left as it's crawling along the surface. So it'll literally chemotax and crawl to where that signal of tissue injury is, or where the microbe is, to where they need to be. Okay? Now, if they stick around for a long period of time, I want to show you this picture, just to show you how potent. We're going to take a break, and we'll take a question. Maybe at the break I can take it. This is a scanning electron micrograph that came off of the cover of a biointerface journal. And this is a hit. This is a cobalt chromium metal hit. Okay, so cobalt chromium is kind of the new titanium as far as cool orthopedic hips are concerned. And this isn't the surface of the moon. These are machined with a smooth surface because as a hip, it's a ball in a socket and you want it to be smooth. Well, post-autopsy, when they took this hip out, right, they see that there's pitting from inflammatory cells called foreign body giant cells, those are those FBGCs. These foreign body giant cells that have stuck around over the lifetime of this hip and have started to slowly chew away the metal. And that's why there's those giant pock marks. So these macrophages can stimulate such digestive strength or destructive strength that a foreign invader, because they don't discriminate between a bacterial cell or a metal implant, they're all foreign, they're not you, and they're trying to chew it up, and that's as far as they got, because it's metal. But is it amazing that foreign body giant cells, which is a bunch of macrophages that have fused together to form a giant cell, they actually can digest away cobalt chromium over about a 20-year period. Okay, that's how long that hip was there. Pretty cool, huh? All right, let's take a quick break, and then we'll come back. Okay.